Welcome to the second lecture of data science. Today we'll be looking at classification in a bit more detail. Now in the last lecture we looked at linear regression. Linear regression is part of the supervised learning, and supervised learning is that technique in which we have the correct labels of the given data during the training time, based on which we can design our algorithm, and this algorithm can then be used for test data. Now, linear regression defines a linear relationship between input variables x, which may be a single variable or a group or set of variables, and some output variable y. Linearity of the linear regression comes from the form or the fact that all of the input variables x hold the power 1 and no greater. Then once you have applied linear regression, we come up with numerous hypotheses. Each hypothesis is equivalent to one solution or one solution in the solution space, and it is our task to find the best of all of these solutions. And then best fit or best solution is found by adjusting the values of weights by using the gradient descent. Gradient descent is an optimization algorithm, and its task is to find the lowest point where in the weights and error space it finds the lowest point where for the given value or any specific values of weights you find the smallest error. Okay, with that we continue to our next topic, which is classification. Now a classifier splits the feature space into regions. Okay, we discussed this in last lecture as well, that given any feature space, a classification algorithm splits this into some one class and some other class. So examples of the positive class would lie in this area, and example of negative class would lie in this area. Understand what it means. In feature space, every dimension is equals to one feature. So if I talk about this line, it would be equal to maybe feature x1. And if I talk about the other dimension, it would maybe be equals to x2. So for every value of x1 and x2, every point over here, every value of x1 or x2, we either call it the positive one or the negative one. So it's the values of the features that help us in determining whether the example lies in the positive region or in the negative region. So again, a classifier partitions your feature space into class label regions. Classification, just like regression, is a form of supervised learning. So again, supervised learning is where we do have the true labels or actual data values for the training data prior to the training. And during the testing, these can be used. So here is a screenshot of a typical training data. This I got from the Iris dataset that is available on the internet. The task over here is to classify flowers or data of flowers into 3 different types based on their sepal width, sepal length, petal width, and petal length. First thing to note is what the features are here. There are 4 features: sepal length, sepal width, petal length, and petal width. And based on these 4 features, we can classify or find the result equals to any one class or category. It can either be Iris setosa or it can be one of the other 2 categories. We have a complete set of such training examples. I've only selected 6 to represent in this slide, but we have a huge set of such training examples, and our classifier would read all of these examples in order to determine for each feature, which value should be the breakpoint, and from the breakpoint we decide the decision boundaries. Okay? So for every one of these features, we decide some criteria that says that inside, if the feature values reside inside this range, then it should be class 1, and if they reside outside this range, then it should be class 2. Another thing, since these are 4 features, so if I could plot this, it would be a 4-dimensional feature space. Since 4-dimensional cannot be represented, so this would be again equals to a hyperspace comprised of 4 different dimensions. So one thing, every feature over here is equals to the attribute that we consider. Second, the number of features that we consider equal to the feature dimensions, and for every value of these features you get 1 point or one example inside the feature space. Boundaries or limits on each of these features determine if the point resides in the first class or positive area or in the negative class. One of the algorithms in the classifier category is the K-nearest neighbor classifier. There are numerous that we use, a simple neural net or perceptron, multi-layer neural net, CNNs, we have RNNs. We have multiple different algorithms that we can utilize for classification. One of the most simplest one is the K-nearest neighbor classifier. Given a training set with classes, data and their labels are known. So once again, this is a classification problem. So this is supervised learning. So we'll have the data sets and we'll have their original labels. Remember this notation from previous. X over here is equals to your input, or this is equals to our feature vector, and Y over here is equals to the output or the correct result. And each of the subscript is equals to the number of examples we have. This can be represented as a superscript as well, and this can be represented as a subscript. The objective over here is decide the class or label of the test vector xt. So next time what the classifier has to do is it would be given xt where it needs to predict yt. Yt is not given to us. Test samples results are not given to us. This is something we need to predict given x of t. And how do we do that? K nearest neighbor, or the method of K nearest neighbor, is to find the distance between the given examples and the new example and then determine the result based on the closeness to the test example. We'll look at it in a little more detail now. So what K nearest neighbor classifier does is it checks the position of the new value in comparison to the positions of the other examples. Let me simplify that. We plot all of the examples in the feature space. So this is a feature space, maybe 3-dimensional, and every point over here is equals to one example. Now, which example are we talking about? The one we had in training data. So all of these are training examples. All of the training examples have their labels, so we can say that these are the red ones and we can say that these are the blue ones. Now, all of this is present online, or we can say that this is in memory right now. Then the new example comes. With this example, we are not sure if this is part of the red ones or if this is part of the blue ones. So what we do is we find or measure the distance of the green example with all of the red ones and all of the blue ones. And then we see if green resembles the blue more, or if it resembles the red more, if it is closer to the red ones or if it is closer to the blue ones. If the distance of green with blue is lesser, we assign the new one as blue. And if the distance of green and red is lesser, then we assign it the class label. This brings us to the point that we understand the NN, or the nearest neighbor part, in K nearest neighbor. But what is the significance of K? So one thing or one question is that how many or which elements to consider when we are considering the smallest distance. So K signifies the number of neighbors or the number of elements you will consider while you're considering the closeness or similarity. Okay? Let me repeat that. For example, if I set K is equals to 1, then only one neighbor would be considered. If I set K equals to 3, then 3 neighbors would be considered, and so on and so forth. So every value of K gives us a radius of the circle among which we are considering our values.